my name is Roy Simpson, and I'm professor of mathematics at Custis River College in Sacramento, California. And this is another proof in my Proofs in Differential Calculus series. And this one is probably one of the most entertaining proofs, in my opinion, in calculus. It's just a fun proof. It's the limit as theta approaches 0 of sine of theta over theta is equal to 1. Now, when you're doing this proof, or prior to doing this proof, you should not have any knowledge of limits or derivatives. Well, you should have knowledge of limits, but not of derivatives of trig functions yet. So that just makes this a little more entertaining if you don't. Our prerequisite knowledge base is going to be limits, just because we're going to need that, and trigonometry, because we're dealing with trig functions, but specifically this is going to have some very kind of high level, not super high level trig, but still you have to be very familiar with trigonometry. The squeeze theorem from calculus is going to be used at some point, and then some geometry is going to be required here. Not a major amount of geometry, just some. So let's go into the proof. I'm just excited to start it. And we're going to start this proof with a nice unit circle and an angle theta. And the terminating side of theta is just going to be this ray that's jumping out here. And we're going to label some points here. For example, that point we're going to call O, as in the origin. We'll call this intersection point A, might as well. It's not that big of a deal. Let's go ahead and draw in here, and it's going to take me a moment to kind of get this done right. But I'm going to draw in here a vertical line so that I get a nice right angle there. Right. We'll call that point B, might as well. Let's see, what else do I want? Oh, you know what I'll do? I'll draw a chord that connects A to this point right here. I'll call this point C. So the point 1, 0, I'm just going to call C in this problem. There's probably a bunch of other things I could draw here. You know what I think I will? I'll draw a couple tangent lines to this curve, and I'll draw those in red. There we go. I went a little color crazy there. Sorry about that, but I just thought, you know what? Because this is such a fun proof to do, I just want to get really crazy with the colors there. So let's see. We have the point O for the origin. We have the point A right there where our ray intersects the unit circle. We have the point B where we have formed a right triangle there. I already mentioned point C is just right there. Let's put a point D right here. Now notice the red line is a tangent line to the circle, and this black line that goes vertical is also a tangent line to the circle, and we'll call point D their intersection. And then I'll also kind of do this one, point E. Do I already have a point E? No, I don't. Point E will be the intersection of the vertical tangent to the ray. That's a lot of fun right there. Okay, so let's talk about some geometry, or trigonometry first. Recall from your good old trig class that on a unit circle, actually on any circle, if you're dealing in the world of radians, arc length is equal to the radius times the angle in radians. So I'm going to let this angle be in radians, and so I'm going to say that theta is equal to the arc length over the radius, but in this case the radius is 1. So it turns out that the arc length itself is just theta. So that's a super important part of this proof. So important, maybe I should really highlight that arc length there is of length theta. There you go, and you can see I did a green shading there on the arc, and I've also written thus the arc A to C is of length theta. Now this is going to be kind of a really cool visual of the squeeze theorem here, because what I'm going to do is I'm going to work on the inside of the circle first, and then I'll work on the outside of the circle with lengths. So let's take a look at what I'm talking about here by starting to work on the inside of the circle. So this altitude, AB, that's the size of that line. The length of that line has to be less than the length of the line AC. Right? And of course, if you look at the length of that line AC, it's definitely shorter than the length of the arc. The arc is always longer than the chord. So that arc length AC also has to be bigger than all that. So we have a triple-sided inequality here. Now, something interesting about this chord length, the pink chord here, is that if you could use a trig function to denote its height. In fact, on a unit circle, the y value, which is the height there, the length from A to B, is always a sine. So, and you can also kind of look at this as the sine is opposite over hypotenuse. So the opposite is this length, the hypotenuse is 1, so the sine is just the length of that opposite side. So there you go. We know the length AB is the sine of theta, and we know that's supposed to be less than the size of the line AC, or the line segment, I should say, AC, which is less than the size or the distance of the arc AC, which we've said was theta. What this basically tells us is that the sine of theta must be less than theta. This is kind of important. This is where we want to go. And if we take a look at what we're dealing with in the proof, let me go back a page here, or 2 pages actually. Sorry about that. We wanted sine theta over theta. So let me go ahead and go forward a couple pages. I'm just going to divide both sides by theta to get the following, that sine of theta over theta, therefore, has to be less than 1. Okay. Now we're going to work on the other side. Now I hope you can agree with me that that arc length from A to C is less than the distance from A to D plus the distance from D to C. I hope you can agree with that, right? That means I'm just taking this red, part of this red line and part of this black line. Those distances should definitely be greater than the arc. However, that distance should also be less than the distance from E to D plus D to C, which is equal to the distance from E to C. Okay, that should make sense, right? That big fat green curve there is, if I stretch it out, it can't be any longer than A to D, D to C. And of course, that length from A to D to C, fun to say that by the way, has to be shorter than E to D to C. That was fun too. Now, as an aside here, I'm going to look at this triangle. Let me highlight the triangle I'm going to look at. That triangle right there. And what I'm going to do is talk about what the tangent of theta is. So if you look at that triangle, the tangent of that angle, theta, should equal opposite over adjacent. The opposite side is the length from E to C. The adjacent side is the length from O to C. However, the length from O to C is 1 because it's a unit circle, so that will imply that the tangent of theta is just equal to the length from E to C. Alright, so now I have something to substitute in for that E to C. We already know the arc length from A to C is theta, so let's just go ahead and write this in. Remember, this is theta, and we just showed that this is tangent of theta. So what does that mean? It means that theta must be smaller than the tangent of theta. Now remember, I want to get a sine over theta in this. So let's see, this is theta is less than sine theta over cosine theta. I'll multiply both sides by the cosine of theta and divide both sides by theta. So I get cosine of theta is less than sine theta over theta. And now I have another inequality. So let me go ahead and highlight the inequalities that I have here. I have that the stuff that's inside my limit is less than 1, but at the same time, the stuff that was inside my limit is greater than the cosine of theta. Remember what I'm trying to do. I'm trying to find the limit as theta goes to 0 of sine theta over theta. So now let's do some mathematics, and I'll actually do the mathematics on this screen. What I might do is move this tan statement here. There we go. And now I'll go ahead and write my statement. So, cosine of theta is less than sine theta over theta, which is less than 1. The limit as theta goes to 0, remember the squeeze theorem of cosine of theta, should therefore be less than the limit as theta goes to 0 of sine theta over theta, which should be less than the limit as theta goes to 0 of 1. As theta approaches 0, cosine approaches 1. As theta approaches 0, 1 is just 1. And so we see that the limit as theta approaches 0 of the middle function here, sine theta over theta, must be 1 as well. So by the squeeze theorem, that limit is equal to 1. And that's what we want. Such a cool proof.